This section is on Rolle's theorem and the mean value theorem. So essentially that is our two objectives. Understand and use Rolle's theorem. Why do we have it? What's it for? Understand and use the mean value theorem. So let's start with Rolle's theorem. So on scratch paper or your OneNote notebook or on this slide right here, plot 2 points that have the same y value. And it can be any 2 points that you want. Notice I've given you one example, -3, 2, and 4, 2. So again, I don't care what the x value is, but these guys have to match up. So feel free to do this yourself, maybe using other points besides the ones I'm showing you. Now I want you to connect those points with a line that's continuous and differentiable. So basically I'm saying, put your pen on one of the dots, do whatever you want in between, but connect it to the other dot. So don't give me a jump or a break or a hole or a gap. So just take your pen and look. That's one example. Now, what we're looking at here says count the number of places between your 2 points that would have a horizontal tangent line. So 1, 2, 3, 4, 5. That's my example. Do that a couple more times and then find out what is true in that situation. So let's erase and try another example. So I always get the students who try to be crafty and they're like, oh yeah, well look at that. Well, guess what the slope of that line is? That slope is 0. Is there a way that I can connect those points where I don't have at some point a tangent line that would have a slope of 0? And the answer is, of course, no. So basically that's exactly what Rolle's theorem says. Rolle's theorem says that there will be at least one horizontal tangent line on a graph that's continuous and differentiable on a closed interval where f of a equals f of b. So again, what does all of that blah 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 mean? If the y values are equal, f of a equals f of b, and it's continuous, like we talked about, don't pick your pen up, and differentiable, so no jumps, graphs, breaks, or pointy lines, then there is going to be some point in that interval at which the derivative is equal to 0. So differentiable is important here as well, because we could have had someone say, okay, well if I have 2 points and I want to connect them, this is an example where it is not going to have a derivative equal to 0 anywhere. And of course, that's also not differentiable at this point. So Rolle's theorem is only when it's differentiable and continuous. So this guy would not count because it's not continuous at that point. Now, before I talk to you about the 3 conditions of Rolle's theorem, let's just remind ourselves that the whole point of Rolle's theorem is to say that if we have the conditions met, we know for sure there'll be at least one critical number. So that is what Rolle's theorem is telling us, which means there is a possible relative min or max at that point. But as we looked at before, it's not guaranteed that there is one. Now, what conditions must be met? Well, it must be continuous, it must be differentiable, and f of a must equal f of b, which means those 2 y values must be equal. Remember that it's still possible to have a critical value at a point if all 3 conditions aren't met. If it is continuous, as my graph is below, if it is f of a still does equal f of b, as my graph does below. But notice this is not differentiable. I can still find that I have a critical value at the point C because f prime of C does not exist. So let's take a look at a Rolle's theorem question together. We are going to find the 2 x-intercepts of this. And of course, why am I finding the 2 x-intercepts? Well, because then I'll know that f of a is equal to f of b, if A and B are both zeros. So again, I'm not going to graph this one specifically, but if we can visualize that this is some sort of quadratic equation, that if I can find A and B by using algebra, of course, then I can say f of A is equal to f of B because they're both equal to 0. And then I can find or show that at some point between those two, there must be a horizontal tangent line. So first let's find the 2 points. So notice I've taken my original equation and I've just set it equal to 0 and factored and found that my 2 points are 1, 2. So redrawing my picture, that's 1, that's 2. We get the idea. We have to basically prove at some point between A and B, there's going to be this guy that is a horizontal tangent line that would tell me that there is a min or max at that point. Obviously, in this case, it would be a minimum. So how do I apply Rolle's theorem? First, I have to prove the 3 conditions. My first condition, it's continuous. Well, if you have a polynomial, like a quadratic, like a cubic, like a quartic, it's always continuous. When do I look at something not being continuous? Well, let's say I had the function 5 over x. This guy is not continuous at 0, so I'd have to really pay attention to the interval. I could still use Raleigh's with this if my interval was, say, 1 to 2, like I'm dealing with now. But if the interval was 0 to 2, then it wouldn't work because it's not continuous at 0. But I digress. Back to my conditions. F is continuous because it's a polynomial, and it's differentiable, again, because it's a polynomial. It's continuous, it's smooth, there's never going to be a point where I'm not going to be able to find the derivative. And then, in fact, I have found the derivative, which is f prime of x equals 2x minus 3, and that's just a nice linear function. So there's no points at which the derivative is going to be undefined in that interval. The last thing I have to show is that f of A is equal to f of B. So remember, this guy is A, this guy is B. So f of 1 is equal to 0 and f of 2 is equal to 0. So this is typically how we write it. F of 1 equals f of 2, they both equal 0. So all I've done now is to say, guess what? I can use Raleigh's theorem. And now I'm going to apply Raleigh's theorem. So Raleigh's theorem says that there's going to be some f prime of c equals 0 for some c but in the interval from 1 to 2. So to find c, I took my derivative and I plugged in 0 for f prime of x because I want to know when does the derivative equal 0, and found that x value is 3 halves. So I used Raleigh's theorem to know that it's existed, and then of course I used algebra and calculus to find the value at which it exists. So here's one more example using Raleigh's theorem. Again, I encourage you to press pause, try this question in its entirety, then press play to see how you did. So in this one, again, we're looking at the function, and we're looking for, this one says all the values of c in the interval such that f prime of c equals 0. So we're looking at the interval -2 to 2. So do the best that you can. Look back at our last example. When you're ready, press play to see how you did. So again, first I'm going to just make sure I can use Raleigh's theorem. So I'm going to say f is continuous because it's polynomial, because it is a polynomial. 2, it's differentiable, again, because it's a polynomial. We don't have to worry about being differentiable when it's a polynomial. And I found the derivative to be 4x cubed minus 4x. For 3, I'm using the 2 endpoints of my interval, -2, 2, making sure that when I plug those values back into my original equation, that those 2 values have the same y value. So again, applying Raleigh's theorem, we know that f prime of x equals 0 for some x. So I know there's at least one. How do I know what they are? Well, then I'm going to take my f prime, which I forgot my prime down here, but f prime of x is equal to 4x cubed minus 4x. I'm setting that equal to 0, and then I'm solving. So I have found, through algebra, 3 points, 3 critical values at which I am going to have a horizontal tangent line.